This video is going to show the reading for pages 1 through 4. Page 5 is on a separate video. Okay, this is titled Molarity. Reflect. Lemonade is a tasty, refreshing drink to enjoy on a hot summer day. Tasty, that is, unless not prepared properly. One person might make a batch of lemonade that has a bland taste. Another person might make a batch using the same ingredients but produce lemonade that is too tart to enjoy. A third person might make a batch that tastes absolutely delicious. What is it about 3 different batches of lemonade, all made using the same ingredients, that give rise to such different results that you can taste? What does this have to do with chemistry? Look at our definition right here. Solution, a mixture of pure substances with a uniform composition. The concentration of a solution. Lemonade is an example of a solution. A substance that is dissolved in a solution is a solute. The substance in which a solute is dissolved is the solvent. In the case of lemonade, the solute is lemon juice and the solvent is water. Sugar is often added to lemonade, and this represents another solute in the lemonade solution. The difference between a sweet glass and a sour glass of lemonade has to do with the amounts of lemon juice and sugar mixed into the solution. The amount of solute present in a solution is the solution's concentration. Solutions are important in chemistry because they are used in many laboratory procedures. When using solutions, chemists need to know the identities of the solutes and solvents in the solutions as well as the concentration of the solutes. Molarity is the concentration of a solution in chemistry. It is defined as the number of moles of solute per liter of solution, or moles per liter. This unit of moles per liter is also called molar. A 2-molar solution of sodium hydroxide, for example, is written as 2 molar NaOH. That would be 2 molar sodium hydroxide. Look out! Molarity is moles of solute per liter of solution, not per liter of solvent. To calculate molarity, do not first measure the volume of the solvent and then add solute to it. The solute particles take up space, and your final solution volume will be a little larger than desired. Instead, begin with the solute and add enough solvent to produce the required amount of solution. A chemist adds the final drops of solvent to make the desired amount of solution. Page 2. What do you think? What is the molarity of a solution made by dissolving 1 mole of solute in enough solvent to produce 1 liter of solution? How does this solution's molarity compare to that of another solution made by dissolving 10 moles of solute in enough solvent to produce 1 liter of solution? Check your answers before the What Do You Know section of this companion. Calculating concentration in units of molarity. Make sure the units are correct when calculating molarity. Suppose a chemist makes a saline solution that contains 23.4 grams of sodium chloride, NaCl, in enough water to produce exactly 275 milliliters of solution. What is the molarity of the solution? Step 1. Determine the amount of solute. The mass of the solute in this problem is given in grams, so it must be converted to moles. To do this, we first need to use atomic masses of sodium, Na, and chlorine, Cl, from the periodic table to calculate the molar mass of NaCl. Formula weight. Formula weight is the same thing as molar mass of Na, and this should be a capital Cl. Okay, so there's the molar mass of sodium chloride. 58.44, like they call it molar mass down here. I don't know why they have to use so many different terms for molar mass, but they mean the same thing. We can use the molar mass to calculate the moles of NaCl, should be a capital C, for the given mass. Okay, so this is just converting grams to moles. Okay, we're used to seeing this as a long line, so a little bit of difference from what we're used to seeing in class. Determine the volume of the solution. The volume of the solution must be converted from milliliters to liters. Okay, you can do this times 1,000 or divided by 1,000 like that, or you can just move the decimal back 1, 2, 3 places, 0.275. Calculate the molarity. We can now use the moles of solute in liters of solution to calculate the molarity of the solution. Okay, so this is our formula. You'll see more detail on this on the math connection paper. The chemist has produced a 1.45 molar saline solution. Like I said, this gives you a brief overview. You're going to get a lot of details on the math connection paper. Okay, page 3. What do you think? Calculating the dilutions of solutions. At the beginning of this companion, we talked about lemonade that did not taste very good because it contained either too much or too little lemon juice. Suppose you had a pitcher of lemonade made with too much lemon juice. You could dilute it by adding water until the lemonade tasted less sour. Dilution is the process of adding solvent to a solution to decrease the concentration of solute. As the illustration at the right shows, adding more solvent to a solution does not change the moles of solute. However, adding more solvent causes the concentration of the solute to decrease. A concentrated solution is diluted by adding more and more solvent. The volume, shown with a capital V, and molarity, capital M, of a solution can be multiplied to give the moles of solute in the solution. Moles of solute equals volume times molarity. During a dilution, the number of moles of solute remains constant. Only the volume and molarity of the solution change. This allows us to write an equation relating initial moles to final moles. Initial moles of solute equals final moles of solute. Substituting the volumes and molarities, we can rewrite this equation as follows. V1M1 equals V2M2. You'll see on their other worksheet they call it VIMI and VFMF. The I is for initial, so initial is first. Final is your ending, in which this case is just second. So sometimes that'll be I's and F's instead of 1's and 2's. Still means the same thing, it's just initial and final when you see that. The subscript 1 describes the initial solution, and the subscript 2 describes the diluted solution. Thus, a dilution calculation is based on the idea that the moles of a solution remain constant, and only the volume and molarity of solution change as the dilution process is carried out. The molarity or required volume of the diluted solution can be calculated from the concentrated solution using the dilution equation. As long as 3 of the 4 variables in the dilution equation are known, the 4th can be calculated. For example, suppose a chemist mixes 250.0 milliliters of a 5 molar solution of hydrochloric acid with 500 milliliters of water. What is the molarity of the diluted solution? Try to solve the problem on your own, then turn to the next page for the answer. It's actually on the next page. I think the page was supposed to end there, but you can pause that and calculate it, and then we've got the answer at the bottom here. The initial volume of molarity are volume 1, 250 milliliters, molarity 1, 5 molar HCl. The final volume is volume 2, 250 milliliters plus 500 milliliters equals 750 milliliters. We can use these values in the dilution equation to calculate the final molarity M2. So V1M1 equals V2M2. They have rearranged the equation to get M2 and then plugged in the variables to get your final answer. Okay, page 4. What do you think? After diluting the solution, the chemist has 1.67 molar hydrochloric acid, or HCl, solution. Notice that it was not necessary to convert the volume of the solution to liters. As long as the volume is decreased by the same unit before and after the dilution, the equation is balanced. Discover science. Dilutions help microbiologists quantify bacteria. Chemists are not the only scientists who use dilutions of solutions in their laboratory procedures. Microbiologists use dilutions of solutions to determine the concentration of bacteria in a particular solution. Specifically, a microbiologist makes a set of serial dilutions so that several diluted solutions are made from a single stock solution. Instead of making each dilution from the stock solution, however, the microbiologist makes serial dilutions by diluting each solution in succession as it is made. In other words, the stock solution is used only for the first dilution. The newly diluted solution serves as the stock solution for the next dilution, and so on. For example, 1 milliliter of the stock solution is diluted to a total final volume of 10 milliliters. Next, 1 milliliter of this diluted solution is diluted to a total final volume of 10 milliliters. A 1 milliliter sample of this diluted solution is further diluted to a total final volume of 10 milliliters. This process continues until a range of diluted solutions has been made. How does this help the microbiologist quantify the bacteria in the original stock solution? The microbiologist spreads each dilution evenly across a separate plate covered with agar, a substance that provides nutrition for the bacteria. The plates are kept warm for a certain time to encourage the bacteria to reproduce and grow. Microbiologists place several dilutions of bacterial solutions onto agar plates to count bacteria. Afterward, the plates reveal a distribution of colonies of bacteria. The more concentrated dilutions are covered with more bacteria. In these plates, there are so many bacteria that individual colonies cannot be counted. At the other end of the dilution spectrum, the plates containing the less concentrated dilutions may not have any bacteria colonies at all. However, at some dilution level between these two extremes, the number of colonies on a plate will be easily counted. Each colony represents one bacterium cell from the original diluted solution. Thus, the microbiologist can use the number of colonies on this plate along with the dilution information to calculate the original concentration of bacteria in the stock solution. Okay, page 5 can be found on a separate video.